Hi everybody, good morning. Welcome to lecture 4. So far in the course we have only discussed how to retrieve data from databases, but we haven't discussed how we can manipulate or modify the data that is already saved in a database. And that's what we're going to be focusing on in this lecture. We are not by no means talking about designing databases or designing tables, because that's a whole separate topic, but it's still useful to understand and learn how we can make certain modifications to the tables that we already have, and also understand the fundamentals of constraints that we apply in those tables on the columns that we have, because this is also tightly connected to the way that we retrieve data from our databases. So that's kind of the idea behind learning about all that in this lecture. Okay, let's get started. So this is the small kind of database that I created in the last lecture, containing a bunch of information about instructors and courses. And we just run this cell. You don't need to worry about what it means at this point. Okay, just have a look. This is the instructor table, and this one is the instructor course table. Okay, the first thing we're going to be looking at is how to insert data into a table that we already have. Okay, so first of all, inserting data into a table requires us to know kind of the structure of the table that we're dealing with. And we have learned that we can inspect the structure of a table, the columns that we have, the data types that we have, using meta commands in pSQL. For example, using the \d followed by the name of the table in pSQL gives us an output like this, which gives us the column names, column types, and also some other information following that. So this is always very helpful, these meta commands, to see what kind of columns we have in our tables. Okay, so first, let's look at the insert statement. So the insert statement can be used to add rows to a table, and we can use it in different ways. We can insert rows by column position, by column name, or we can insert rows from another table into our current table. Let's see how that works. So this is the syntax for the insert statement using column position. So insert into table name, and then values. The values is also a keyword. And then inside a set of parentheses, we basically just list the column values that we have. And the values will be assigned from left to right. The order matters here because this is by column position. If we don't provide values for certain columns, then those values will be set to null by default. So let's see an example here. Here I'm inserting this particular row into my instructor table. Okay, the ID, the name, email, phone number, and the department. Let's do that. It says one row affected, meaning that our work involved one row. And now let's insert another row. This one doesn't contain information about phone number and department. And let's see how SQL handles that. So both of these statements are working. Now let's take a look at the instructor table. And now if we go all the way at the bottom, we see these two rows that are inserted into our table, and you can see that for the columns that I didn't provide any values, it's filled with nulls. Okay. These are the insert statements that we used. Okay. So one thing to notice is that we shouldn't really think that the new rows will show up at the end of our table. This is just how it works in this particular example. It might not be this way in another table in another situation. Okay. Now the other alternative way to insert rows into a table is by column name. This one makes it easier to understand what we're doing because we're basically providing column names and then we're inserting values based on those. So here, table name followed by the columns that we want to insert values in, and then the rest of it is the same as the above. Let's see an example here. So here, instead of just mentioning the table name, we also have a list of columns for which we want to list values for. Department, name, email, and ID. And let's do that. Okay, mathematics Carl, and here is Carl from the math department. And you can see that although we haven't inserted the column values in the order that they appear in the table, they have still been inserted in the right order because we have been doing the insert based on column names. Okay, now let's see what happens if we insert just the value for just one column. If we do that, what we expect is to get nulls for all of the rest of the values, and this is in fact what we get. So 999 is what we inserted, and all of the other columns will be filled with nulls, as we can see here. Okay. It's also possible to insert multiple rows at once, and if you happen to download like a SQL file off the internet to create a local database, this is what usually SQL files contain. So insert into a table followed by a bunch of values listed as such, as you can see here on the screen. So this is one tuple, two tuples, three tuples, basically rows, and it works pretty much in the same way that it works for single rows. Okay. Just remember to separate the different rows with commas here. The other very useful way is to insert values into a table from another table. And the syntax works like this. So insert into table name, and then we list the column names as before, but instead of having the keyword values in there, we use a select statement. So we select a bunch of rows from another table and we say, okay, take these rows, insert it into the table that I have here. Here's an example. So I'm creating a new table called visiting instructors. Okay, and then I'm inserting these values. Okay, let's check out the table. Okay, 2 visiting instructors here in the visiting instructor table. And now, let's suppose that these visiting instructors have accepted a permanent position and we want to move these rows from this table to the instructors table that we already had. So in that case, what we can do is that we can say, okay, insert into the instructor table what we already had, and then instead of listing the rows manually here, we're just selecting from the visiting instructor table. We're selecting everything from this table. Okay, and now if you check out the instructor table, all the way at the bottom after the null values that we inserted previously, we can see the new instructors that we have from the other table. And the values, the columns that we didn't list any values for, those are filled with nulls. So let's take a look at the SQL statement again. So the insert statement followed by a select statement. Okay, just remember that there's no need for column names to be the same between the source table and the destination folder and the destination table. Okay. All right, any questions so far? Yes.
You mentioned in the note that there's no guarantee that the roles are inserted after everything. Is there a way to like force it to always be on the bottom?
Yeah, so the question is, I mentioned that there is no guarantee that the inserted rows will appear at the bottom of the table. And the question is there a way to enforce that? Basically, in a relational database, no, because that is something that the database engine decides. Suppose that you have a very large table and the database is saving different parts of the table in different parts of the hard drive. That order might depend on that. So we don't have any control over what the database engine internally does. So yeah, there's no way. Okay, let's move on. Now, what about a situation when we want to update some of the column values for the rows that we already have in our table? And we have this update statement, very commonly used when you have a database running in the backend of, for example, a website or something like that. We're constantly updating our table. So update table name, and then we use the set keyword, and then we list the column names followed by whatever we want to update that column with. And then we can also have a where statement. That's optional, but that's usually what happens. We want to update certain rows, not all of the rows, usually. For example, in this table that we have, these new instructors, they're not assigned to any particular department. And suppose that I want to assign them to the business department, for example. What I can do is to use this, update instructor table, and then set department to business, but not on the like all of the rows, but where the department column is null and name is not null. So that basically gives us these two rows. Name not null, so it means that it don't select this one. And department is null, meaning that only pick these two rows. And if we do that, it does what it's supposed to do. And then these instructors will be assigned to the business school. Let's take a look at the SQL statement again. Okay, so one thing to remember and pay attention to is that the statements that we have been running so far in SQL were all select statements, which are not dangerous. However, the statements that we learned in this lecture, they can be dangerous if you run them without really being sure about what you're doing, because they modify the tables that we have. A query is just a query. It just returns a bunch of results to you. But these statements can actually be dangerous. However, the thing is, running these particular statements, like update statement or insert statement or anything like that, requires certain privileges, which means that probably if I don't know how to use those commands, I probably don't have the privileges, so nothing to really worry about that much. But still, it's something good to know and worth considering. Okay, so similar to update and insert, we also have a command. We also have a statement for deleting rows, and that's the delete statement. Very straightforward syntax. Delete from table where a certain condition is true. And yeah, for example, we can remove that one row which had an ID of 999. Do that. That one disappears. It was this one over here. And if we check out the table, we can see that that one is gone. So straightforward. Nothing really too special here. Okay. And now suppose that I want to remove the newly hired instructors from the visiting instructor table. So previously we had these two rows, and if I do delete from visiting instructors without a condition, everything will be deleted. Do that, run this again. Now all of the rows are gone. An important thing to note is that when you delete rows from a table, the table structure is still there. It doesn't mean that you're deleting the table. You're just deleting the rows inside of that table. The table is still there. You can still insert values into that table. Okay, similar to the delete statement, a question that I've seen to be popular on tests and database interviews is the difference between delete and this statement called truncate. So, truncate statement is used to remove or delete all of the rows in a table without having any conditions. So it's similar to delete without a where condition. But the thing is, with delete, because the database engine works row by row, it can be slow to use delete. However, truncate knows in advance that everything is going to be gone. So it's more efficient and faster if you want to just get rid of each and every row inside of a table. Basically, the way that the database engine works, and we will talk about this a little bit in next lectures, is that when it works on a particular row, it locks that row and until this user finishes the operation, whatever the person is doing, that row won't be unlocked. So when you run the delete statement, because it works row by row, it locks every row so that no other person or user can access that row, and then remove that, and then goes to the next one, locks it, and then removes it, and goes to the next one. So it's going to be a little slow. However, with truncate, it just locks the entire table at once and removes all of the rows at once. The other thing is that with most database operation, not most, probably all database operations, there is the database engine keeps a log of what's happening, what has happened in the past. And with the delete statement, it keeps a log of every row being deleted, so there is a write operation happening in the background. With truncate, there is only just one log operation, one writing operation happening in the background. That's considered just one operation. With delete, if you have 10 million rows, that would be 10 million write operations just for the log. So that's the difference. Truncate removes all of the rows. It's more efficient. It's faster because it works on the entire table simultaneously. However, with delete, we're going to work row by row and remove the rows. Okay, just one note here about the dangerous nature of these commands. But again, if you have those privileges, chances are that you already know what you're doing, so that makes sense. Okay. I have an optional part here. So with all of these commands that we have learned, insert, update, delete, you can also optionally use this returning keyword. And what it does is, for example, it inserts or updates some of the rows or deletes some of the rows, and then it returns whatever row that it has done some operations on. For example, sometimes you're deleting some of the rows inside of your table, but maybe you want to use another table as a recycle bin kind of thing. And once you delete it from here, you just want them to be moved to another table that you're going to deal with later. So in that case, you can run your delete statement using this returning keyword, and then return everything that's going to be deleted and move it into another table. Here, the example is about updating. So for example, here I'm updating the instructor table, setting the department to stats for all the rows which have department set to be statistics, so just a minor change. However, I'm also returning all of those rows. And when we do that, instead of just saying 2 rows affected, it also shows us which rows have been affected. It's even nice just to see what's going on not just for situations when we want to do something with the rows. So these are the ones that have been updated. Okay, so question. Did you notice what happened to these two rows? So if I go back to the instructors table, I have Alexei and Vincenzo here, right? And now I have them here. So those rows have been moved. And this is what I was warning you about all along, that the location of the rows inside of a table in a relational database is not reliable. We cannot say that those rows are always going to be there. With an update statement in this case, the order of the rows have been is just changed. So we can't rely on that. Okay. Any questions before moving on to the next section about any of these statements? Insert, update, delete, truncate. All right. Yeah.
So the returning statements, in terms of rows that have been affected before they were affected?
No, after. So once it does that operation, then the rows are going to be returned to you to do. Yeah.
So I understand that, like it makes sense there. But how would we then set it to?
Oh, okay. That's. Yeah, good question. Because it's SQL, it's not like we save it in a variable or something and then use it, right? So, okay. We do something similar to what we have done here. Let me go back. Okay, so you can see that here we have a select statement which basically gives us some rows. So we can kind of take that bit that was deleting stuff or updating stuff and use it over here in order to insert those results into some other table. And we will see an example of that later in this lecture. Yep. Okay. All right, so this part is done. Just really a bunch of syntax. Not much more than that, but the important part is coming up. Creating, modifying, and dropping tables. Okay, just as I mentioned before, designing a relational database involves a number of steps. There's usually a design step called normalization. I don't know if you're familiar with that. If you have taken a database course before, probably you know about that. It's the process of deciding what columns you want to have in your tables, what tables you're going to have, in the way that the table structure is the most optimized, is as optimized as possible. That process is called normalization. We won't discuss that because it's quite involved, and this is not the objective of this course. We're not going to be designing databases using the knowledge that we learn here. But just know that that's a different thing. Here we just wanted to get a little bit familiar with the kind of constraints we have for tables, how to create and drop simple tables, and so on. Just the basic knowledge that would help us with data retrieval as well. All right. So, first thing, creating tables. This is the syntax. Create table, followed by the table name, and then column names. Each column is followed by its data type, and then followed by some constraints. Okay, so it looks straightforward. Now let's see an example here. Suppose that we have a table called customer, and it basically just stores information about customers that we have for an online store. We have customer ID, title, first name, last name, address, town, all of those columns. And for each one of the columns, I, as a database administrator or designer, I choose these particular data types for each column. For example, I choose integer for customer ID. That's the right data type. I choose this char data type for title, and yeah, other data types as well. So this is basically the syntax. And this just defines the table, the columns, and the data types, nothing else. Now we get to the discussion of integrity constraints, and this is an important one. So one of the main reasons that we use databases is to make sure that is always consistent with the constraints that we have in mind. For example, we have seen instances of such constraints. For example, the data type of each column is a kind of loose constraint because it decides what kind of data you can insert into a column. And that's something desirable. That is something very desirable. We've talked about it that for example, in pandas, if you want to do something like that, you have to write your own code saying that, okay, if you want to insert some data into this data frame, you have to check the data type first and then give that error or this error if the user doesn't behave nicely. So in that case, we have to do all that kind of stuff. But in a relational database, for example, we have this domain constraint or the data type constraint. We say that this column should only store integers. This column should only store strings. And that's something very desirable. However, as I said, this is a loose kind of constraint. We want to have more control over what we do with our data, and we want to make sure that it always adheres to the standards that we have in mind for the data. Okay, so we collectively call these constraints integrity constraints. And now let's see the different types of these constraints. All right. So the first integrity constraint is called primary key. So a key is one or a set of columns or attributes that uniquely identifies a row in a table. So in the relational model, we have to be able to identify each row by at least one column or a collection of columns. So we have to have an identifier that we can certainly say, okay, this is the identifier of that row. If you give that identifier to me, I can retrieve that row for you. I'm not going to retrieve multiple rows or no rows for you. I have the identifier. That's called a primary key. Okay, so a primary key has to be unique. And when we place that constraint on a column, it cannot be null. Those are the two very important features of a primary key column. It cannot be null, it cannot be empty, and it should be unique. Okay, how can we enforce that constraint on a column? Here, for example, we can either use this syntax or this syntax. So column, data type, what we have already discussed, and then followed by this keyword, these two keywords, primary key. This is called a column level constraint because we're defining it when we are defining the column. However, we can also define it as a table level constraint here at the bottom once we're done defining the columns. And the difference is that when we define it like this, it's only applied to one column. When we define it like this, we can apply that to multiple columns. That's the difference. So this is table level, that's column level. Okay. Yes.
When would we want a primary key on multiple columns?
Yeah, sometimes it's not the case that one of the columns can uniquely identify the row, but a combination of the columns does that for us. So instead of defining a whole new column to store just something like ID, instead we take a combination of, let's say, two columns in order to uniquely identify that row. Yeah. So that introduces a lot of redundancy if we just introduce a column just to store, for example, IDs. Okay. So here's an example with the customer table. You can see the column name, the data type, and we say, okay, this customer ID is going to be the primary key, is what identifies each individual row in our table. We can also, instead of this, we can do this. These two are equivalent in this instance because there's just one column, and then we're applying the primary key on that one column. So these two are equivalent. Okay. So with the primary key, what we usually would like to do is to have a data type that increments the values automatically once we insert new rows into our table. So instead of just each time manually inserting the ID, we can set a particular data type that basically just automatically increments that ID for us, and that's in Postgres, it's called a serial data type. So if I have, instead of saying integer, if I have serial, then Postgres knows to basically auto-increment that column value as we progressively add more rows to our table. So for example, here I'm creating a demo serial table and I'm setting ID as serial. I can also say primary key. And then I'm inserting these rows into my table. So I'm just specifying the column name, and let's see what happens. Note that I haven't defined the ID column here. I only have defined the name column. But when I check out my table, I can see that the ID column has been automatically incremented. So this is, again, something very commonly used in the backend engines of websites. For example, when you sign up for a particular website, this is usually how they store your information. They have an auto-incrementing ID column that takes care of that for them. Okay, so that was it about primary keys. Any questions? So the primary key constraint is called a key constraint, basically, which imposes two constraints, basically, uniqueness and non-nullability. Okay, let me drop this one. Now, okay, so before talking about foreign keys, let's take the break here for 5 minutes, and then we'll be back with our discussion. All right, we're back. So far we've discussed different types of constraints for our tables in order to maintain the consistency and integrity of our database. Before talking about foreign keys, I wanted to mention that the general idea here is that the kind of operations or checks or the things that we do about data, which is solely related to data storage, has to happen on the database side. So it's possible to not have all of these sophisticated ways of maintaining the integrity of database and then just write code in Python when we retrieve data or when we insert data and write code in Python to do these checks. But that won't be ideal. We want to bundle related things together. We have kind of worked with this idea, worked based on this idea in Python when we worked with classes. We wanted related things to be in one place together. We don't want things to be scattered around. And this is why we do this. We have these constraints in our database management system instead of doing it inside of our programming language. So kind of the philosophy of why this is the case here. Okay, so another type of constraint is a foreign key constraint. So we have seen joins so far a lot in the lab and also in the previous lecture. And you know that at this point, the joins rely on the fact that we have some common column values between different tables. That's how joins work. Because, we do the join on the equality between these two column values. That's what we do. Meaning that if the column values are not consistent, then the join operation wouldn't work as expected. So the foreign key constraint does exactly this kind of check. It makes sure that the columns that we want them to be related, it makes sure that those values are consistent between different tables. For example, if you remember, in the world database, we have a column called country code, or code, I guess. And in the city table, we have a column called country code. Code in one side, country code on the other side. And we know that these two columns are related, and we know that when we try to join these two tables together, we use that column to do the join, right? So the database designer knows this in advance, knows that, okay, I'm having these two tables, the user is going to be joining these two tables, usually using these two columns. There are other columns that you can do the join, but this is usually what happens. So I have to make sure that the values truly correspond between these two columns. Okay, so the foreign key is there to make sure that those values are consistent between different tables. So let's see how that works. Okay, so in order to tell you how this works, first we need this terminology here. A child table is a table containing a foreign key, and a parent table is a table which a foreign key in another table references. What does that mean? So in the world database, we have a column called code. And in the city database, we have a column called country code. And we can kind of say, okay, this country code column in the city table references the values in the code column in the country table, right? So we have two tables. We know that in the country table, we have this column called code, and we have a city table. And here we have a column called country code. And we know that the values in here, this value references some value over here, okay? So in that case, we call this the child table, and we call this the parent table. Okay. All right, so basically these values should correspond to these values in a logical way. Now let's see how we can define that before talking about how this, what this means in practical terms. So suppose that we have here a table, the column, data type, primary key. However, on the second column here, we have the column name, the data type, the constraint, and then we have this added bit here. It says this column 2 references column 1 from table 1. Okay, so it's basically trying to implement this kind of constraint that we have. Okay, so this column references another column in another table. Okay, we can define it as a column level constraint or as a table level constraint. That doesn't matter at this point. So let's see an example here. We had a customer table that we have defined before, storing information about customers. Okay, and here I have an order info table, okay, which stores information about orders that people make. And in order to maintain consistency between these two tables, I want to make sure that the customer ID here is actually a customer ID that exists in the customer table. That's what this constraint means. So by this, I mean that whenever a user or a client tries to insert a row into this table, into this order table, then the database engine is going to check, is this customer ID an ID that exists in my customer table? If yes, then it's going to go ahead and insert that row here. If not, it doesn't. So the whole purpose is that we don't want to create orphan childs. Okay, so if a row here has a customer ID that doesn't exist in the parent table, it means that I have created some inconsistent data. And when we do the join, then the joins don't work as expected. So that's the purpose of a foreign key constraint. Okay, so I'm going to let that sink in for a bit. Questions? Yes?
So you said you're doing this effectively to check if the things correspond.
Right.
Is that like, correct me if I'm wrong, that's, you're not creating this table to save it in the database, though, because this table that you're building could basically be by query without looking at more database space, right?
Can you repeat the last bit?
What I mean is, so you said, I understand the purpose of like using this to check things correspond.
Right.
But with the relational database, the purpose is like not storing duplicate values.
Sure.
Because you can pull different columns, and that's the whole point. It doesn't duplicate things.
Sure.
So you're not using this and then like saving it back to the database as a new table because it contains entirely derived values, right? And if you wanted this information, like the user wanted it, they could make a query to produce the same table without creating a table. But this is the check, what I'm saying, not the save.
Okay. Okay. So suppose that we have these two tables already. Okay, so I need to store the city information here, the country information here, right? And I want to make sure that when I enter a new city in this table, the country code corresponds to an existing code here. Okay, so in that context, what are the duplicates? You mean that we have to duplicate the country code here? We have.
What I mean is, so you're doing it to check to make sure that it works correctly.
The constraint is there to check,
But
yes.
you're not taking the child table and inputting it to the database. So that's redundant.
Okay, we're not taking the child table and putting it into the database. Yes, we have the child table in the database, right? We already have this child table. It's only the constraint that we put there in order to be like an agent telling us if you insert a row.
Wrong word. When you make this order info table, right? This is a new table, right?
Yeah, okay. So do you mean that we have to create this constraint when we create the table? Is that the question? Is that the confusion?
What I mean is like you're creating so you have the parent and the child, and the parent and child work together.
Okay.
To make this new table. This is local, right? This is local
Okay.
But then you don't fit back into the database itself. Then it's with the combined table or the child. Maybe
I don't understand the question quite precisely. Okay, so again, let me just summarize the process. When we design the database, we know that we're going to have a country table, a city table, and at that point, we're going to put that constraint there in order to make sure that when we populate the database, those two tables, inconsistencies don't have a way to happen. So the tables are there, structure is there, we can start inserting rows into the tables. Okay, we can discuss this later after the lecture. Yes?
How does it handle it when you actually try to insert a new value without the correct reference?
Okay. Great question. We're gonna get to that point in a bit. So the question is, what does the database do if we actually insert an inconsistent value that violates this constraint? So there are different options available to us, basically. We can set the constraint such that it just gives an error. We can set the constraint such that it makes a decision that is consistent with the constraint that we have, or it sets some default values, sets some null values. We have the ability to do that. Yeah. Okay. So other questions? So I hope we're clear on the purpose of having this foreign key constraint there. It's there as a check to see that the value that you're inserting in a particular column corresponds to the same value in another column in another table. So that, for example, here, you don't insert a city and then by mistake you insert a country code that doesn't exist. Because in that case, then that row would just create problems for us, right? Okay. All right. Okay, so now let's quickly see what kind of changes would trigger a foreign key constraint check. Okay, the first situation is when we try to insert or update a new row in the child table, meaning that here I have the city table, I insert a new row, so the database gets triggered because it says, okay, I have to check the country code to make sure that it corresponds to a value here. Or if I'm updating one of these rows, it again has to check. So that triggers a constraint check. Or if I delete or update a row in the parent table. So here, if I update the code for a particular country to something else, then this foreign key constraint becomes triggered. It will be checked to see if it makes, if it basically makes an orphan child here in the other row. So these two kinds of operations, they trigger the check on the foreign key constraint. Okay, but there are other operations that won't trigger any checks. For example, if you insert a new row in the parent table, if you insert a new country here, that doesn't trigger any checks because that's just a new row here, and whether or not, I mean, the country code could be anything. Another type of operation that wouldn't trigger any checks is deleting a row in the child table. Here, if I remove the row pertaining to one of the cities, it doesn't trigger any checks because there's no possibility of making inconsistencies. Okay. Okay. Yes. Yeah, great question. Yeah. So the question is, here I have this sentence here that says that foreign key values could be null or duplicate, and this is not something that can happen with primary keys. And I've just said that this references a primary key, a unique key probably in another table. So how can that be null? This happens when we actually delete something from here, and then we specify that whenever the parent row is deleted, I want this one to be set to null. This is something that we decide about, and we'll get to that in a bit. Yeah. Okay. And foreign keys can be duplicates. As you remember, in the city table, we have a bunch of cities for each country, so they can be duplicates. There's no problem about that. Okay. Now, so this whole topic is called referential integrity, meaning that we're trying to maintain the integrity between tables, okay? And now we have referential actions, a functionality provided to us by relational databases, and that's okay whenever basically a violation of a referential constraint happens. What do I want to do? So there are different scenarios that can happen, different ways of handling this. Okay, we can use these keywords on update, on delete, followed by some set of actions. For example, let me just show you the code first. So here I have this constraint, foreign key, and then references, this particular column, and then I have a referential action here. I say that when delete or on delete, cascade. Let's see what that means. So we have on delete or on update, and then followed by a number of actions that we can see here. So no action means that if a violation happens, then just show an error message. Don't proceed, just show an error message, no action. Okay. So cascade applies the same change to the child row. Meaning that, for example, if you do on delete cascade, it means that if you remove one of these countries, then remove its cities as well. Okay, so cascading the changes down to the child table. We also have set null. So okay, if you remove, for example, the country here, then set all of the country codes here to be null. So we don't really want to remove those rows. We still want to keep them, but set them to null as an indicator that this was something that once had a parent row. Now it doesn't. Okay, and then we can also do set default, meaning that take some default, set the foreign key value to its default value. Okay, so we're going to see later on that we can set default values for columns, and this is what it does. It says that if the parent is deleted, set this column to its default value. The default value might be, I don't know, 0, empty string, whatever you like. Okay, one important thing here to note is that the referential actions, as well as the foreign key constraints, they are defined in the child table, not in the parent table. Okay, so that's important to remember. All right, so what we have seen here, an example of referential action. Again, we have this order info table, and then we know that this customer ID here should correspond to the customer ID in the customer table. So this is why it says references customer ID, and it says on delete cascade, meaning that if somebody deletes one of the customers in the customer table, then just delete the order info as well. On delete cascade the changes down to the child table. Okay, so a few things about this syntax. So the keyword constraint here. Okay, so this is the name of the constraint. It's not necessary to specify that yourself. If you don't, it just gives it a default value. And then we have foreign key that's necessary. And then this is the column that we set the foreign key on. And then references is necessary. Then this is the target table, and this is the target column. And this is the referential action statement. Okay, so I want to show you these constraints using pSQL on the tables that we already have. So for example, here, this is the world database. I have a bunch of tables here. And if I do \d on, let's say, city, let's do country language. Okay, you can see that along with the column names and column data types, we also see foreign key constraint here. Okay, it says that this table has a foreign key constraint on the country code here that references the code in the country table. So whenever you do this \d followed by the table, you also see a list of the constraints that are set on that table. Okay. All right, questions? Yes.
Can these constraints be created after creating?
Good question. Can these constraints be created after the tables are created? Yes, we have a special command, special statement for that called alter, and I'll get to that in a bit. Yeah, so we can do that. Any other questions about foreign key constraints? All right, let's move on. All right, so the other type of constraints that we're going to be discussing are pretty straightforward. This unique constraint just makes sure that the column that you specify this constraint on, the values in there remain unique. You can't insert duplicate values. And you can just specify that by having this keyword in front of the data type for a column. And similar to other constraints, you can set the constraint on multiple columns if you specify that as a table constraint. Nothing really quite interesting here, just that it makes the column values unique. Okay, not null. Similarly, it ensures that the values in a particular column cannot be null. Okay, and this default constraint. So we can also set a default value for all columns. By default, the default value for all of the columns is null. So you saw that when we insert a row and we don't specify column values, the values would be null. You can specify that to be something else. For example, in this column, I say that whenever nothing is inserted here, the default value should be a string n/a, for example. Okay. Or here I have a column that has a data type of timestamp, and I say, okay, whenever the client doesn't insert a value, just use the current timestamp at this moment that the row is being inserted. And you can imagine that this has a lot of applications in, for example, logging operations in a system. You don't insert any values, and that by default, the timestamp would be set to the current moment in time. Okay. All right. We also have this very helpful statement called check. And we have already learned that the data type kind of provides us with some level of control over what kind of values could be inserted into a column, but that's a very loose constraint. We can have more control using this check. For example, if I set the values in a column to be integers, okay, that's good. But what if I want those integers to be between 1 and 100? Then I can use the check statement here in order to enforce that condition. And the way that we do that, similar to other constraints, we put it in front of the column name and data type. And then the condition in a check constraint can be any condition that you can use in a where clause. As simple as that. For example, here in the customer table, I have this phone number column, and I want to check that the format is something like this. So I want to be sure that the number format is 3 digits, hyphen, 3 digits, hyphen, and then 4 digits. So check that phone is like that string. Okay, and if it doesn't follow that, if it violates that constraint, then the client would get an error, and then we're sure that we never insert inconsistent values into our table. Okay. All right. Questions before moving on to the next topic? Yes?
For a column, say suppose the column has a constraint not null, what would be the default value for the column?
If the column cannot be null. Okay, so if you the question is, if a column has a constraint of not null, then we can insert null. What happens if we try to insert a value? So you'll get an error, basically. That's what happens. It doesn't allow you to do that. That's the good thing about maintaining data in a database. You can never violate the constraints that are already there.
So we can't assign a default value for the column.
Pardon me?
So say suppose in the case like we can't assign a default value to the column.
You can do that, but the null.
We can't So what would be the default value by default?
So you can default yourself in that situation. Okay, you say non-null. Okay. All right, so we are done with constraints. Any doubts, questions? All right, let's move on. Okay, so something very helpful that we have at our disposal when using most relational databases is the concept of temporary tables. And a temporary table behaves just like any other table in your database, with the difference that it only persists during, for the duration of a session. Meaning that if I create a temporary table right now to store some intermediate results, intermediate rows, results of a query or something like that, I can create a temporary table for that, store the results, but as soon as I disconnect from my database, as soon as I restart my Jupyter Notebook session, or if I disconnect from my pSQL, the temporary table will be gone. So it's very helpful to store some intermediate results and to speed up the kind of operations that you're doing, but it gets rid of the entire table, just destroys it as soon as the session is over. Okay. Where can this be helpful? Sometimes the queries that we run are pretty complex and they take a lot of time to be processed. It's not unusual for a query to take hours to be processed. So when you do that, it's not like here that we get back like 200 rows and we can do that instantly. So if we've spent 3 hours, sometimes we want to save that result somewhere. So we can create a temporary table for that, store the results in there, and then use those results to run some other types of queries. Okay. So the syntax is that create temporary table exactly similar to how you create other tables, with the difference that you use this temporary keyword. But usually we don't create temporary tables like this. Usually what we do is that create temporary table, and then we use a query in order to populate the temporary table. So the query can be any query that we have learned so far. Okay, so just put the query here. For example, here, create temporary table temp instructor as this query, meaning that run that query, store the results into this temporary table. Okay, let's run this. And now this is my temporary table. And that's all right. This results from my intermediate, these intermediate results are saved into this temporary folder. Okay, now this code cell, you don't need to worry about what it means and how it's constructed. It just gives us a list of the tables that we have right now. Okay, because I don't have access to pSQL commands inside of my Jupyter Notebook, this is why I use this code here. So you don't need to worry about that. It's just for getting a list of tables. Okay, long story short, this is the list of tables. You can see the temporary instructor table appearing there. But I've said that these temporary tables only exist for the duration of a session and only in this particular session. So it means that if I connect to my MDS database here, okay, and now if I check the tables that I have in this database, you do not see temp instructor table here because this pSQL that I'm running here is a different connection. It's a different client. So this client has no clue that there is a temporary instructor table for another client because that's not a persistent table, okay? So that's the whole point of it. No temporary instructor table here. Okay. All right. So now let's discuss a little bit how we can modify tables that we already have related to some of the questions that were posed before. So it's ideal to specify all of the design constraints when we create our tables in the database, but the world is not ideal, so sometimes we have to make some decisions, make some changes after we have created our tables, after we have data in our tables already. So in that situation, we have this SQL statement called alter table, which we can use in order to basically alter our tables, to make changes to the table structure, not the data, table structure. We can use that to add or drop or rename columns, change data types, or add or change constraints, rename entire tables. We can do all of that. However, again, similar to the previous cases, we have to have the required privileges in order to be able to do that, because this is kind of a dangerous operation. Okay, so the syntax is alter table, table name, and then followed by an action. And this is just the example list of actions that we can do. For example, add column, and then data type and the constraints. Or we can alter an existing column and then set different constraints for that. We can drop a column, as you can see here. We can drop a constraint, as you can see here. Okay, let me show you an example. So this is our instructor table, just 5 rows. And then suppose that I don't need this phone number column, and I can do alter table instructor, and then the action is drop column phone. And when we do that, if we check out the table again, you can see that this phone column is gone. That's the whole purpose of it. One other example could be to add a constraint, for example, on this email column. Suppose that I want to follow this particular pattern. And I can do alter table instructor, and this is my action. Add constraint, this is the name of the constraint, and this is my actual constraint. So check email is like this pattern. So some characters followed by an @ sign and then followed by some other characters. Okay. All right, let me run this actually. So first, let me show you the instructor table. Instructor table, okay. For the instructor table, you can see that I only have this primary key constraint. Okay, and now if I run this, just to show you that it actually works, now we have this constraint over here. So we had an existing table, and then we added a constraint on top of it. Okay. So any questions about the alter command? All right. Okay, one problem that we may encounter while altering a table is that, for example, if you add a constraint to an existing table, that constraint might be violated just right away because some of the values don't adhere to that constraint. So in that case, let me update our instructor course table to set the instructor ID to null for particular instructors, just a change. And then now, because I add this foreign key constraint in my instructor course table, this right now wouldn't work because I'm introducing this foreign key constraint, and this references the ID column here. And then, let's see that. Oh, yeah, that works. Yeah, sorry. This one works. Let's check the addition of this condition here. Instructor course. Okay. And then we can see the foreign constraint has been added. Okay. These are the courses that we had. And now, okay. Right now that I have a constraint as a foreign key, I'm trying to change the ID of one of the instructors. And this is a situation that I said, if I change some row in the parent folder, then the referential integrity check will be triggered. So it will be checked. So if I do this update, and then now you can see that the ID has changed, and all right, and you can see that the courses that were taught by this person, which was me, are set a value of null for their instructor ID. So this is an example of this constraint. I say onDelete set null. And what it does is that it sets these instructor IDs to null because I have changed the ID of this instructor over here. Right here. So this is an example of cascading the changes down to the child table. Okay. So one last example here. I want to test the constraint onDelete set null here. Okay. So if I do delete from instructors where name is equal Arman, it gets rid of that row in my table. And now if I check out this one, I can see that all of the courses that were taught by me are assigned a value of null. Okay. Yeah, this is just another example of adding this constraint to the country table. You can check that out later. This constraint actually doesn't exist, the one that I discussed. You can add it using this code that you see over here. Okay, last thing to discuss today is about dropping tables. And there's really not much to discuss about it except for one note here. So let's check out the syntax here. Drop table, and then we can drop multiple tables together. The syntax is as straightforward as it looks here. This, if exists, what it does is that if the table doesn't exist, it doesn't throw an error. That's the only purpose of that. Other than that, if the table exists, it just drops that if you have those privileges. However, there's a situation that if the table that you're deleting has some child tables that reference that table, then the drop table command wouldn't work. Okay, so in that case, if we are sure that we want to get rid of that table and also the constraints that are set to reference that table, we can use this keyword cascade. And then in that case, it not only deletes the table, but it also drops any constraints that depend on that table. And if you try to create and remove tables with constraints, you will gonna have to use this command a lot. You have to use drop table cascade. Otherwise, the tables won't be deleted. So here's a list of the tables that I have at the moment. And now, let's drop table visiting instructor. That works because no other table depends on that. Now let's retrieve the set of tables again. This is reduced to 3 instead of 4 that we had at the top. Okay. Now, finally, let's drop the table instructor. Would this one work if I don't have cascade? No, because I have another table that references this one. So it wouldn't work. So I have to use this cascade keyword over here. If I run that without the cascade, what it tells me is if I use it like this, it will tell me constraint FK instructed on table instruct courses depend on this table. But if I use cascade, I do that table is gone along with the constraints. I can also drop multiple tables, and here I get rid of all of the tables that I've created so far. And now, final thing, no tables in the database anymore. 1 minute for any last questions. Yes?
A lot of content, like theory and code. Any tips on what to study for next week?
For next week, okay. I wouldn't worry too much about the syntax. This is not something that I'm personally interested in. You can always check out the documentation. But concepts like for example, the foreign key constraint is pretty important, I guess. The primary key, the importance of it, and basically everything that surrounds that. That's what matters to me because that's tightly knit to the concept of a relational database. Yeah. Yeah.